Hello, 5th graders, and welcome to a read aloud of today's science ebook titled Understanding Our Sun, as needed for today's science lesson, Unit 5, Lesson 2, called The Sun. So what is the sun like? Let's read to find out. Read in pages 4 through 19 of the ebook today. So let's get straight to it, open it up. And going straight to page 4, where we can start with Chapter 1, Our Amazing Sun. Our solar system is our home in the universe. As well as Earth, it comprises 7 other planets, dozens of dwarf planets and moons, and millions of asteroids and comets flying around. At the center of everything is the sun. It makes up 99.8% of all of the mass in our solar system. Its gravity keeps Earth and other objects in predictable orbits, which are regular paths around the sun. The surface of the sun is around 9,932 degrees Fahrenheit, or about 5,500 degrees Celsius, and its energy gives us light and heat. At the center, our sun is a star, like one of about 250 billion other stars in the galaxy, the Milky Way galaxy. Each star is surrounded by its own solar system of planets and other objects. Along with the moon, the sun is one of the easiest celestial objects, or objects in the sky, to see from Earth. It is only in the past couple of centuries, however, that people have looked at the sun in a scientific way. They ask questions about the sun's physical qualities. How was it created? Why is it so hot? Has it changed? Will it continue to change? So Earth's atmosphere, we're told, is an envelope of gases that surround the planet. The atmosphere distorts the sun's light, making it look as though it has rays. We're also told that scientists darken bright images of the sun to reveal details of the activity on its surface. So that's how the sun actually looks in detail. It is impossible to send spacecraft to the sun. It is too hot for anything to approach without being destroyed. But by studying the sun with different scientific instruments, people have come to know a lot about it. We know what it is made of. We know that it is 4.603 billion years old, which is more than 60 million years older than the Earth. Many questions still remain, however. Scientists are just beginning to unravel the secrets of the sun. New discoveries. Careful observation and advanced technology reveal new information about the sun. Astronomers are scientists who study space. Using the Hinode spacecraft, they found that the sun's surface bristles with jets of X-rays. These jets fire blobs of energy off the surface at about 1.9 million miles per hour, or 3.2 million kilometers per hour. Even after centuries of watching the sun, our star continues to surprise us. Indeed, still a lot we don't know about the sun, but we're learning more all the time. The all-important sun. So how important is our sun to our planet? All life on Earth exists because of the sun. The sun gives out energy in the form of light and heat. This energy supports all life on Earth. It warms the oceans and the atmosphere. Green plants convert sunlight into food for themselves and for animals through photosynthesis. The sun's gravity also holds Earth in its regular orbit. If Earth drifted out of its orbit and off into space, the planet would become bitterly cold, and all life would end. The center of it all. More than 4.6 billion years ago, our solar system did not yet exist. There was nothing but a cloud of gas and dust. This interstellar dust occurs throughout our galaxy. As gas and dust clumped together at the center of this cloud, it formed a star. As the star attracted more material, its gravity grew stronger. This gravity made the cloud around it spin. More clumps of matter became planets and dwarf planets. They were made from the same materials as the sun itself. The sun generates a huge amount of energy and magnetism. Magnetism is a force that attracts or repels other objects. Magnets, like magnets. The sun's magnetism forms the heliosheath. This is a magnetic field that extends beyond our solar system. This acts as a shield to protect our solar system from harmful cosmic radiation from deep space. So we're told here the sun's magnetic field may protect our whole solar system as it orbits the center of the Milky Way galaxy. So there's our sun right there, and all of the 8 planets that orbit the sun, or revolve around it in big orbits or big circles: Mercury, Venus, Earth, where we live, Mars, Jupiter, Saturn, Uranus, and Neptune. not to mention a bunch of other dwarf planets like Pluto. We're also told about 10% of the stars in our Milky Way galaxy are yellow dwarfs, just like our Sun. So our Sun is a yellow dwarf star. Dwarfs and giants. The Sun is a G-type main sequence star, also known as a yellow dwarf. This is a type of star that is a little more than 1,000,000 times larger than Earth. More than 70% of the Sun is made up of hydrogen gas, which acts as the fuel for the star. Most of the rest is helium, another type of gas, with small amounts of other elements. Yellow dwarfs can keep burning their hydrogen for up to 10 billion years. Many stars in the universe are bigger and burn brighter than yellow dwarfs. These stars, called giants, supergiants, and hypergiants, only last for a few million years before they run out of fuel. Other stars, called red dwarfs, last much longer, but do not burn as brightly. By providing a lot of energy, but also burning for billions of years, the Sun may be an ideal star for supporting life on the planets that orbit around it. Well, life for our planet anyway. If there's life on other planets in our solar system, we don't know about it yet. So why study the Sun? It is difficult to study the Sun. It shines so brightly and can blind anyone who looks directly at it. Astronomers use special filters to protect their eyes or from harmful light. They also study the Sun using instruments to detect invisible radiation, such as X-rays. This has allowed them to understand a lot more about the Sun. They have figured out that Earth is lucky to be in a part of our solar system called the Goldilocks Zone. The Goldilocks Zone. This means that Earth is not so far from the Sun that we freeze, but also not so close to the Sun that it makes it too hot for anything to live. So we're not too cold, we're not too far away or too cold, not too close or too hot, we're just right. Just the right distance to be able to survive. So the power of the Sun. Earth and everyone on it depends on the Sun. It has existed longer than Earth, and it is easy to assume that it will always be there. In fact, the Sun is a huge explosion that has been burning for more than 4.6 billion years. Eventually, it will run out of fuel and die, so it will not always be there. Our Sun, just like any star, will eventually run out of fuel and fizzle out one day, but not for a very, very long time. Every second, Earth receives enough energy from the Sun to light 17.4 quadrillion light bulbs. A quadrillion is a 1 followed by 15 zeros. A small backyard receives enough solar energy to power 10 houses for the whole day. So the Sun gives a lot of energy. We're also told solar flares, those big explosions erupting from the Sun's surface, are up to 35 times the diameter of Earth. So very, very big. Only about 1/1000th of the energy of the Sun reaches Earth. The way the Sun releases its energy is inconsistent. Sunspots, solar flares, and changes within the Sun can unleash coronal mass ejections, or CMEs, which are jets of energy. If these charged particles hit Earth, they could destroy electric grids, or electricity grids. The power system could be out for years. That kind of thing has actually happened before. A need to know. Astronomers observe the Sun closely through special telescopes and solar observatories, on Earth and in space. Not only does studying the Sun tell us more about other stars in the sky, but it can also help predict future changes in the Sun's behavior. This might allow us to be better prepared for whatever our nearest star throws at us. Chapter 2. Looking at the Sun. Today, most scientists believe that our Sun is more than 4.6 billion years old. They believe it formed from a giant spinning cloud of dust and gas called a solar nebula. Gravity pulled the gas and dust together, which made the nebula spin faster. This flattened the nebula into a disk and pulled material toward the center. Eventually, this material grew so big and dense that it formed a star. The atoms of hydrogen inside were pressed so tightly together that they fused or joined to form helium. This nuclear fusion releases huge amounts of energy in many forms, including light and heat. So nuclear fusion is basically what fuels the Sun and keeps it growing, keeps it burning and keeps it growing bigger and bigger. Looking back in time, there is plenty of evidence around our solar system to show how old it is. Using special dating methods, scientists have learned that none of the Earth's rocks are more than 4.6 billion years old. Neither are any meteorites, which are pieces of rock that fall to Earth from space. So if there are no rocks on Earth or even meteorites older than 4.6 billion years old, that must mean that that's about how old our solar system is. The Sun and other bodies of our solar system also have to obey physical laws, which shape how bodies move and interact. Scientists are able to test and explore these laws by carrying out experiments, but also by using mathematics, which predicts the orbits of the planets. Mathematicians used computer programs to show how the Sun and the planets interacted with each other over millions of years. They helped them figure out when the planets began moving around the Sun as our solar system took shape. Scientists have also figured out what the Sun is made of and how much energy it gives out. By calculating how much hydrogen the Sun has as fuel, they discovered how long it would continue to burn. Looking at the stars. Astronomers also study stars other than the Sun. Earth's galaxy has around 250 billion stars. Many are the same size as the Sun and burn in a similar fashion. Astronomers use telescopes to study the development of these stars. This shows them how stars are created and also how they eventually die. So there's a picture of a solar nebula right there, spinning into a disk, encouraging the growth of a star and the formation of the planets. So our Sun and all of our planets originally formed through a solar nebula like this. Just a bunch of gas and dust particles. We're also told that the European Union, so that being several countries in Europe, the United States, Canada, Japan, South Korea, Taiwan, and Chile, built the ALMA together, which is the Atacama Large Millimeter Array. So it's basically a huge telescope that's used to take pictures of the Sun. Understanding the Sun. Ancient peoples knew very little about the Sun, but they did know that it was important to life because it provided light and heat. Many viewed the Sun as a god. Then early astronomers looked closer. They noticed how the Sun's position in the sky changed in a predictable way over the seasons. The Babylonians, ancient peoples, lived in what is now Iraq, in the Middle East. In the 1700s BCE, so about 1300 years ago, they were among the first people to record solar eclipses, when the moon passes between the Earth and the Sun. Babylonian astronomers learned to predict when eclipses would occur again. The ancient Greeks were the first to observe sunspots. The Greeks believed the Sun was another planet, like Mars and Venus. Obviously, we know better than that now. New understanding. Around 270 BCE, Greek astronomers suggested that the Sun was at the center of our solar system and not the Earth. When Christian religion began, it claimed that Earth was at the center. It was only in the 1500s when the Polish astronomer Nicolaus Copernicus put forward a mathematical model of our solar system in which the planets orbited the Sun. Other astronomers, such as Galileo Galilei, used the newly invented telescope to gather evidence to support this model. In 1687, the English scientist Isaac Newton published calculations based on his theory of gravity. He showed how Copernicus's model could work. So at one time, people thought that the Earth was the center of the solar system, but through the use of science and mathematics, we then discovered, with the help of these scientists, that it was actually the Sun. So looking into the Sun, in 1800, British astronomer William Herschel discovered infrared radiation from the Sun. Scientists realized that the Sun was producing energy they could not see, including infrared and ultraviolet radiation, X-rays, and even gamma rays, forms of radiation. This discovery gave scientists the first clues about what the Sun was made of. When white light passes through a prism, like this, in this picture right there, that's a prism, which is a triangle made of glass, it splits into different colors, like a rainbow. Splitting sunlight, however, reveals dark bands in this rainbow. Scientists discovered that these dark bands are caused when parts of the light are absorbed by different atoms. In the Sun's case, the bands matched where light is absorbed when it hits atoms of hydrogen and helium. This technique is called spectroscopy. So, through the use of spectroscopy, they were able to discover that the Sun was made primarily of hydrogen and helium, those two gases. Scientists use spectroscopy to identify the makeup of distant stars and the planets that orbit them. Such techniques and observations through telescopes allowed scientists to learn how old the Sun was and how it burned. Astronomers were limited to observing the Sun from Earth, but when it became possible to go into space, more mysteries were revealed. So here we have a model of the solar system from the 1800s, about 12,000 years ago. I'm sorry, 1200 years ago, which placed Earth at the center and the other planets outside of it. But obviously we know that that's not how it is now. We know it should be the sun in the center, with Earth surrounding it. There's William Herschel, the British scientist there, who discovered different types of radiation coming from the sun. And there's a picture of that prism right there. Isaac Newton used a prism to split white light into different colors. Next up, the sun and the earth. For viewers on Earth, the light of the sun interacts with the atmosphere. This is because Earth's atmosphere acts like a prism and scatters sunlight into a rainbow. The blue and violet colors bend the farthest, while orange and red bend the least. When the sun is low in the sky, its light has to pass through more of the atmosphere to reach Earth. The air catches the light and scatters it like a prism. The blue, green, and yellow light are bent away from the viewer's eyes, leaving mostly orange and red. So this is why sunsets and sunrises often appear red, or kind of orange. This effect is heightened if there are particles of pollution or dust in the atmosphere. They scatter the light farther. This is known as Rayleigh scattering. So is the sun really yellow? Turns out the sun is actually white, but we'll see why it appears yellow. At noon, sunlight appears white. Okay. Most people, however, think of the sun as being yellow. It may be that once the sun has moved low enough in the sky to look at, its light scatters enough to make it look yellow. The same scattering also explains why the sky looks blue. Blue light bends farther when it is scattered and fills the sky. Purple light bends even more, so the sky could be purple. However, our eyes are more sensitive to blue light than purple light, so that's why the sky appears blue. You actually see sunlight a few minutes before the sun rises or after it sets, because the atmosphere bends sunlight over the horizon. We're also told here a green flash is a type of mirage caused by the way light bends as it passes through different layers of Earth's atmosphere. So, in very rare cases, one might see the sun appear as kind of like a green flash very briefly. So this scattering also causes an effect called the green flash. If conditions are right, such as over a clear horizon like an ocean, the setting or rising sun can turn green for a couple of seconds. Green flashes are often seen by pilots, especially those flying west towards the sun, which slows the apparent sunset. So what are solar eclipses then? The sun is responsible for another big event for sun watchers on Earth, a solar eclipse. This is when the moon passes between the Earth and the sun at the right distance for the moon's shadow to fall across a part of the Earth. Eclipses alarmed early peoples, who thought they were signs of disaster. However, the Babylonians could accurately predict solar eclipses by 1300 BC. So, about 700 years ago, they were able to start doing that. It was not until 1605 that astronomer Johannes Kepler described why a solar eclipse occurs. Edmund Halley predicted the arrival of a total eclipse by May 3rd, 1715. He was off by just 4 minutes. So very accurate prediction there. So if you've ever seen a solar eclipse, the moon passes in front of the sun and blocks it for a few seconds. So we're told here the beads of light seen around the edge of a solar eclipse are the sun's light, shining past the mountains on the moon. So if you ever get a chance to see one of those, it's pretty amazing, a solar eclipse. Observing the sun. Even though scientists make their discoveries through observation, it is never safe to look directly at the sun. Even just after a solar eclipse, the light from the sun is so bright that it can damage people's eyes. Sunlight is so intense that lenses can focus it into a beam that burns things and damages equipment. Astronomers observe the sun using special filters to block most of its light. Cameras can also snap pictures very quickly, so they capture just a fraction of a second of light on film. Unlike regular telescopes, large solar telescopes have to compensate for the sun's heat. The sun can cause movement in the air, or the heat can cause movement in the air, which changes the image. Solar observatories are usually located in towers and painted white to keep things cool. Solar telescopes were placed atop high mountains to avoid the atmosphere bending the light. So scientists can use filters like on big telescopes like this to take pictures of the sun, both to reduce its brightness and as a shield against invisible infrared and ultraviolet light, those forms of radiation that is found in sunlight. Solar discoveries. Solar observations from Earth were enough to show that the sun was not a simple disk of light. Astronomers could see sunspots and solar features such as flares on its surface. By studying these features, astronomers figured out that the star takes 24.47 Earth days to rotate at its equator, or widest section, by up to 38 days at its poles. As technology improved, astronomers made more discoveries. In 1942, solar signals were jammed due to radio waves from a large solar flare. Today, astronomers use radio telescopes to monitor solar flares. The way these sound and radio waves pass through the sun also tells scientists a lot about what is going on inside the sun, where hydrogen is turned into helium. Telescopes in space. To get even better views of the sun, astronomers have had to go to space. Skylab was a space station that included a solar observatory. It orbited Earth between 1973 and 1979. Skylab took more than 150,000 photographs of the sun, including X-ray and ultraviolet images. It recorded spectacular solar flares rising from the sun's surface. In 2008, the Fermi Gamma Ray Space Telescope began orbiting Earth and measured gamma rays put out by the sun. This type of radiation is more energetic than light or even X-rays. In 2012, the telescope detected a solar eruption that produced gamma rays with 2 billion times the energy of visible light. So scientists inserted an image of the Earth into this picture to show its size relative to the sun. So if the sun is this big, then next to it the Earth would be just a little tiny speck right there. It's much, much bigger than the sun. I think about 1 million times as big as the Earth. And final pages here, ships to the sun. Astronomers would like to send space probes with instruments to gather information from the sun. Missions to the sun are rare, however, because the sun's heat makes them very difficult. Between 1965 and 1968, Pioneers 6, 7, 8, and 9, space probes, orbited the sun at distances as close as 0.75 atomic units, a bit further out than Venus. These were the first probes to measure the sun's magnetic field and its solar wind. The solar wind is a stream of particles released from the sun's corona, or upper atmosphere. Between 2011 and 2015, NASA's MESSENGER probe orbited Mercury, with an orbit that kept it on the night side for long periods of time to allow the probe to cool from the sun's heat. It got within 0.30 astronomical units of the sun and measured the energy of solar flares. So I think that probe is the one that has gotten the closest to the sun. Parker Space Probe. So this one right here is a picture of the Parker Space Probe. It has a heat shield that's 4.5 inches thick to protect its instruments. Very necessary when it gets close to the sun. In August 2018, NASA launched the Parker Solar Probe. It was the first mission designed to fly into the sun's corona, orbiting 3.8 million miles, or 6.2 million kilometers above the surface. Astronomers hoped that the mission would answer questions about why the sun's corona is much hotter than its surface. Lagrange points. In 2018, ESA revealed plans for a new solar mission. If it receives approval, this mission will launch 4 probes from Earth in the 2020s. These probes would orbit the sun at 2 special points in Earth's orbit around the sun, where gravity of the Earth and the gravity of the sun are perfectly balanced. These positions are called Lagrange points. Similar positions exist between any 2 bodies in space where one orbits the other. Earth has 5 Lagrange points, which are known as L1 to L5. The mission is planned to visit 2 of them. These are L1, directly between Earth and Sun, and L5, which follows Earth's orbit, but is 45 degrees away. The probes would measure the speed of the solar wind, observe the sun's corona, and look for solar flares and coronal mass ejections that may be heading from the sun towards Earth. So as for whether this mission has started, I'm not sure yet. Perhaps that's something you could look up on Google. Look up Lagrange points probes to see if those 4 probes have been launched from Earth to start that mission. One way or another, I'll leave that up to you to research if you wish. For now, that will conclude our reading of our science ebook for today called The Sun. Thank you for joining us today, and we'll see you in the next one. Take care. Goodbye, everybody.